So right now, it's a great pleasure to introduce Fernando Brandao also at Amazon Web Services, and he California Institute of Technology. And he has done great work in different areas of physics, including quantum simulators, quantum computing, and quantum information, et cetera, et cetera. And he's going to be talking today about an important topic on fault-tolerant quantum computing using bosonic qubits. Please go ahead, Fernando.
Thanks. Thanks, Franco. Hi, everyone. It's great to be here. I wish I was in person with you. I couldn't join in person, but still, it's nice to be here giving this talk. And please interrupt me if you have questions during the talk. You can send a message, or you can just say out loud. So I want to talk about fault-tolerant quantum computing with bosonic systems. I didn't know Helmut was speaking before, so maybe that's I'm repeating what he said. But anyway, I want to start with a slide on what we are doing on quantum computing at Amazon Web Services, right? So there's Amazon. You all know Amazon Web Services, the part of the company that does cloud computing. Is the biggest provider of cloud computing today. And 3 years ago, the company decided to start doing development in quantum computing. And there is 4 activities going on right now in the company. The first, starting here from the top, is what we call Amazon Bracket. And that's a service offering current quantum hardware integrated in the AWS clouds. So basically, via the cloud, you can access some early quantum hardware that many companies have today, right? So there is IONS with IonQ, there is D-Wave there is Rigetti for superconducting qubits, there is photonic systems, Xanadu, and a few others. Sorry, what happened? I pressed something wrong here. Then there is, let me go counterclockwise. There is what Helmut talked about, which is the Amazon Quantum Solutions Lab. And that's a team of researchers led by Helmut, working on research program with customers, right? So basically customers from Amazon, they're interested in quantum computing, in the future impact of quantum computing. And the Quantum Solution Lab allows customers to engage with Amazon, figuring out how quantum computing might impact their business in the future. Then very recently, it was announced like a month ago, there's the AWS Center for Quantum Networking. We have an internal team, and also this is done in collaboration with researchers at Harvard. So our team is in Boston in this case, and they basically work on future quantum networking technologies, on quantum repeaters, on quantum key distribution, and so on. And there is a part of the operation that I'm associated with, which is the AWS Center for Quantum Computing. And this is a team, most of us are here on Caltech campus in Pasadena, California, but there's also people in other places. And our long-term goal is to build a fault-tolerant quantum computer, which we think is necessary for giving quantum advantage to society and industry. So let me just talk a little bit about this, like, the question that we get asked all the time at Amazon and as a community, right, we get asked on a daily basis today is where and when will quantum computing make a difference, right? And maybe our answers today are similar to, there's this quote by Alan Turing. I don't know if it's true, but many people said that it happened, right? And it's the following. So he was asked around 45, Dr. Turing, where will computing make a difference? And he said, well, I'm not sure, right? So early on, maybe breaking codes, well, which is what he was using computers back then, right? During the Second World War. And I think we're in a similar situation, right? We don't really know what these quantum computers will be useful for. We know they can break codes, right? They can break RSA and many other similar codes, public crypto codes. But what else, right? Impactful. And first, we don't know much, but what we know is also pretty nuanced, right? What is the potential applications, which makes it interesting. And the way to explain it, I think, is to have a figure of merits in our minds. So one is the number of qubits of our quantum device. The other one is the gate error rate, right? So how many gates you can apply without having an error. And the second one, which is very important too, sometimes is a bit overglossed, but it's very important, is what is the clock speed of our gates, right? And where we are today or where we'll be like, in the next few years is like this near term. From terms of qubits, we have device from like 50, maybe 100. We can go to thousands, I think, in a few years. Gate error rates, we are getting close to 10 to the minus 3 today, right? We as a community, I say, right, in different platforms. We're not there yet, we're getting close to 10 to minus 3. If you're lucky, I think we can get 10 to minus 4, maybe 5 years, kind of like, at the physical level. But I want to consider something between like 10 to minus 3 and 10 to minus 5 for this first like area, right? And the clock speed, superconducting qubits, if you implement the gate on the physical level, is like a few dozen nanoseconds, or like 12 nanoseconds, the fastest. So like 10 to the minus 8 seconds, right? If you go to ions, which is lower, is more like 10 to the minus 3 seconds, or like a millisecond. So the gate varies between these, right? And if you're in this situation where we are today, and we're going to be in the next few years, we're in this kind of in a grim situation, I think, in terms of finding potential applications. So there is no guarantees, right, that we can do anything. There is a very serious uphill battle with noise that we have to face. But there is still some heuristics, right, that can be tried in some niche areas, right? So quantum simulations in particular might give some interesting results for some kind of analog simulation. There's, of course, a D-Wave device, right, that try to do some heuristic optimization, as I think Helmut was mentioning, is a bit unlikely that this will give value. But anyway, right, this is like some exploratory phase, right? Then suppose we keep around the same number of qubits from 100 to thousands, but for some reason we have much more accurate gates. We can get like gates, 10 to the minus 10 error rate, 10 to the minus 9, something like this, right? Then we can apply like 1 billion operations without having an error. And suppose the clock speed is not terrible. It's like, from 10 to the minus 6, 10 to the minus 4. So imagine the clock speed of our classic computers is 1 nanosecond, 10 to the minus 9. So I'm telling you, okay, quantum can be way slower, but not like super slow, right? So like 10 to the minus 4, 10 to the minus 6. Then from what we know today, there will be applications of this kind of device, but this will be this target exponential quantum speedups that we learn, right? So there is quantum simulation here, of course, will be universal quantum simulation, which will be exciting, I think. There is, of course, breaking public crypto, which maybe by then, we have post-quantum cryptography anyway, but and what else, right? It's a very interesting question, theoretical question, to see if there is anything else that we can do with exponential speed up. Because then, even if the clock speed of the quantum device is substantially lower than the clock speed of our classical devices, we can still get a speed up, right? This is long-term, right? How we get this 10 to the minus 10 error rates, there is only one path that we're going to discuss next. Even to go beyond like 10 to the minus 4, I think error rate, this will likely require a quantum error correction. Right? And I'll discuss what this means. That's the topic of the talk. But that's kind of where we would like to be, right? So maybe in 10 years or 15 years, I don't know how long, we'd like to be in this like middle, right, row here, and that will be pretty exciting. Now, we can even expect more, right? So say, okay, how can quantum computing be useful more generally, like for more widespread applications? And there is potential for that, but it's even harder to see how it can come around, and it's even longer term. Suppose we have like around like also 1,000 qubits or more. Gate error rates are also very small, 10 to the minus 10. But not the clock speeds, like you have very accurate gates, but also very fast gates, right? From like 1 nanosecond to 100 nanoseconds, something like this. Then, we can run a bunch of quantum algorithms that we know with polynomial speedup. I mean, most of them based on like Grover search and variants of it. And we could get some speedups smaller, but some speedups. What is a challenge of this last one is that from the potential, from the candidates for hardware for building a quantum computer that we have today, and from the schemes for error correction that we have today, there is no way, there is no path for getting to this 10 to the minus 10 gate error rate and clock speed of 10 to the minus 9 or 10 to the minus 8. So there will be, we require advance both in error correction and in like faster quantum gates or different hardware to reach this goal. So I think it's like, even further away, but it's good to have in mind, right? That it's like where we eventually would like to be as a technology, if possible. All right, so we have error correction. That's great. What's like in a nutshell is the idea of error correction? Well, so we try to implement our physical gates, but there will be a limit to how we can improve them in the lab on the physical level. But we like to have even more accurate gates. So what we do, instead of having 1 qubit to encode the information, we have many qubits, and then we store our quantum information in a redundant way there in these many qubits. And then we can form from many physical qubits a logical qubit, which can be, protected from noise in this distributed way. And then we can implement logical gates, which can be very, very accurate. And there's many ways of doing that, right? That's an idea that is known classically for a long time, of course. Whenever we store something in our hard disk, we have to use error correction or send through our optical fiber. This will start to be figured out in quantum mechanics like 20 years ago, and there was theoretical understanding that could be done. Around like maybe also like some 18 years ago, Alexei Kitaev found a code which still today is one of the most promising ways of doing quantum error correction, which is called the surface code. And the idea here is this picture on the right. You have a square lattice for your qubits. For example, in this case, it's 5 by 5 lattice. So you have 25 physical qubits per logical qubit in this example. You need even more qubits because you need what we call some ancilla qubits to measure some information about errors in this logical qubit without perturbing the data qubits. So the idea, similar to like a repetition code, is that you have your data qubits, they are these black points. You have your ancilla qubits, they are the white points, the white dots. And then we measure some 4-body operators between the data qubits using these ancilla qubits. Just apply some CNOTs between them and then measure, or some CZ between them and measure. And then we can get some parity information about, right, this like 4 neighboring data qubits. And from that, we can infer if an error happened or not. And I don't want to explain detail, but what happens here is a nice exponential suppression of errors in the distance of the code, in Z. So you can compute that the logical probability of error, this first equation, will be like some constant A that we can compute numerically. And then the physical probability of error of your gates, your measurement, right, and preparation and so on. I assume they're all the same here, but if they are different, just sum all this exponential decays. And then divided by, very important, some constant, which we call threshold probability. And this whole thing to the power of Z plus 1/2. So it's exponential decrease in distance, which is great, but there is only a decrease if your physical probability of errors is below this P threshold, right? So error correction only works if the individual components are good enough. Otherwise, just errors add up. So what is the surface code? That's like some empirical result, and it's just approximate. Assume some depolarized noise model, which is not the most realistic, but just for some, just have some numbers in mind. The threshold is like around 0.7%. Okay, so you need your individual components to be better than 0.7% to have an improvement, and if they are, you start seeing something interesting. And what this means, like I just, this table I just put, right, this formula for some numbers. Suppose you want to get to, like where we think we can go, where we think we're heading to in maybe a year or a couple of years as a community, like physical error rates 10 to the -3, right? That will be pretty exciting. Then you see that if you want to get to a regime where you can start running some applications, which is around logical error rates 10 to the -8, you require distance 15, and therefore you require 450 physical qubits per logical qubit, right? So that's fine, but it's a significant overhead, right? So you need like for each qubit you had in your quantum algorithm, now suddenly you need 450 physical qubits in the lab, right? So that's fine. So, one strategy is very clear. Use the surface code, try to improve P physical as much as you can, and then just scale up the system, right, and get to the required logical error rates. So let me just go through this because to get some time. Now, there is alternatives for building a fault-tolerant quantum computer, and sometimes this is known as like hardware-efficient error correction. And the mantra here is that you try to correct as much as possible in the hardware level, right? So kind of for surface code, you imagine that you build a qubit whatever way you want, and then once this qubit is there is a probability of error there, a physical probability of error. Then you just scale up and you go from there. But what if, like, you can have a different way of doing error correction, maybe using, for example, the Majorana qubit is a well-known example, right, where maybe your qubits is built from actually like 4 Majorana, right, qubits, or 4 Majorana particles on the edge of 2 semiconductor wires. And then there is hope, although it hasn't been demonstrated experimentally yet, that this could lead to more robust qubits, and therefore, right, using some slight variation of surface code, lead to a fault-tolerant quantum computer with less overhead. 0 pi qubit is another example. And there's this cat qubits, which I want to focus in this talk, which is kind of, instead of using a qubit, you use a harmonic oscillator to encode your quantum information. So you use a quantum system of infinitely many levels, and you try to use this extra space that you have there to do some error correction before you use the surface code. And the question is if this can be helpful for what you want to do, and if it can, lead to a better way of building a quantum computer. So what's the basic idea? So what is like we can call multi-qubits quantum error correction? You have a bunch of physical qubits, right? For example, think about the physical qubits in the surface code, and they form one logical qubit, right? And this is a quantum error correction code. So the individual components, they are like these two-level quantum systems. What's the idea of bosonic quantum error correction? Now, instead of like a collection of qubits, you have one quantum object, one quantum degree of freedom, but this is a bosonic quantum degree of freedom. So like a harmonic oscillator, sorry. So you have infinitely many energy levels equally spaced, right? For example, it can be just some electromagnetic cavity, right? Strip line cavity. There is some microwave like photons bouncing back and forth. This will be the Hilbert space there. Of course, not infinitely many levels, right? Because there's an energy cutoff, but there's a lot of levels that you can use. And then you want to use this extra space that we have here of not having two-level systems, but having many level systems to do some clever encoding of the information and try to get a bosonic logical qubit, which has some protection. So you want to protect a carefully chosen two-dimensional subspace of an infinite dimensional bosonic Hilbert space, right? So there's some recent reviews you can check on this topic. It's an old topic, like first ideas also dating, I'll give a reference later, but almost 20 years ago, roughly as well. And there's many variants, right? So usually they have these very nice pictures where you have, when should I finish? I forgot to keep track of time. Just to plan here. Anyone has I think he's not there. Okay, so
therefore, your talk needs to end 9:05, something like this. So that's California time. So therefore, there is time.
9:05. So you say I have 10 minutes.
Yeah, I think so. Yeah.
Okay.
Actually,
so I have to.
You actually have more than that because you did not start in time.
Oh, sorry.
Well, you can end at 9:10. Thanks.
Or later,
9:10,
okay. You started later. Okay, so whatever he's keeping or the track of the time better. Okay.
Yeah, 9:10 is better. So here's some examples of these bosonic qubits, and I will focus, because of time, I'll focus on one of them only. But and usually how you can have a picture view of a pictorial view of them is you just draw the Wigner function, right, of this qubit, this harmonic oscillator. So it's phase space like P and Q, and then you have like this nice shape. So one way is like called 4-component cat codes. There's binomial codes. There's GKP code. There's 2-component cat codes. And they are implemented in the lab, this kind of qubits. So there's a lot of interesting work coming from Yale lab, Shokop, and Devoret group. Also in France now, in Lecter's group. There's also a group in China working on it, and many other places. So this is really proliferating, number of groups working on this. So I don't want to discuss the details of this experiment. I'll discuss just of one of them, but it's like actively experimentally as well. But what I want to focus here, before giving a specific example of a cat code, is that it's not really a dichotomy between a multi-qubit QEC and a bosonic QEC, because a multi-qubit QEC, like a surface code, like you can always increase the distance and reduce further the logical error rate, right? So it's like a scalable approach for reducing the logical error rate as much as you can, as much as you want, right? Unless there is some correlated errors or something like this. Whereas bosonic error correction, you can apply it, you can get a reduction, and you see sometimes we do get a reduction, but there's no like scalable way of keep getting a reduction, right? So really the way to think about that is that we to build a fault-tolerant quantum computer, you would concatenate a bosonic QEC encoding at the first level, and then later use a multi-qubit QEC, where each one of these kind of qubits in the multi-qubit QEC now is a bosonic logical qubit, right? So some kind of concatenated code where the first code is bosonic, But why you want to do that? Well, because this bosonic system usually is there, right? For you, it's not too hard to get it. So it's a way of trying to extract more juice from the hardware. All right, so that's the idea, right? So like, you have the same thing as the multi-qubit QC, but now each qubit is a bosonic qubit now, which is just this clever encoding of a particular two-dimensional subspace of the bosonic qubit space that we had here. Right, so just like the approach, right, that I discussed before for surface code, right, which is a valid approach, and maybe it's the best one with the jury's out there still, is that let me focus on superconducting qubits here, because it's what we're doing at Amazon, but of course you could do with ions or spin qubits, whatever you want. So here we have the surface code, and each qubit would just be the first two levels of a transmon qubits, right? This gives pretty good qubits. Of course, each transmon is not protected by QC. There's also no particular noise structure there usually. And then, right, to get the protection from, the collection of these transmons. Another approach that we like to study here is that we have the surface code as well, or some variant of surface codes. But now each qubit is not a transmon, is actually a bosonic qubit, right, encoded in this two-dimensional qubit space of this bosonic two-dimensional subspace of this bosonic qubit space, right? And then we want to see, right, if we can get some gain from this. I wanted to discuss two approaches, but I'll jump the first one. So one way to do that is to use GKP qubits, and they are nice qubits, bosonic qubits. They were proposed many years ago by Gottesman, Kitaev, and Prescu. And one work we did recently, theoretical, and also other groups did, is that we can, once we do the concatenation of GKP with surface codes, we can use some analog information that we can get from the GKP codes and use it together with the decoding of the surface code and get very significant improvements in the logical probability of error, like many orders of magnitudes. There is some drawbacks as well. For example, the time it takes to prepare the GKP ancillary states. But I think it's kind of a promising direction. More work is needed and experimental work in particular, but we saw some potential gains there. I will jump this. And I want to focus on another one, which is a two-component cat qubit. And the idea here is to try to get a large noise bias between X and Z error, and then explore that to have a more economical surface code, which is what I want to focus here. We wrote a paper a couple of years ago, was published recently, then also some follow-up on some different qubits, and there's another one coming. And we are building some experiments on this that I want to mention very quickly. One plot to you. So let me not discuss this because of time. And let me go to the two-component cat qubits. All right. So what is the idea here is that suppose you have your harmonic oscillator and you have a coherent state, right? It's just a kind of a classical looking like state of lights there, right? Or whatever, if you have some vibration, state of the vibration. And then you just choose some coherent state alpha with amplitude alpha. And now you consider two states. One is plus alpha, the other is minus alpha. So same amplitude, same mean photon number alpha square, but different phase. And these states are not really orthogonal, but if alpha is like kind of large, they are pretty orthogonal, right? So the overlap decreases exponentially in 4 alpha square. And then we can say that our 0 state is like roughly plus alpha, and our 1 is roughly minus alpha. It's just roughly because they're not really orthogonal, but you can define precisely in the complementary basis if you want. The plus state you can say is plus alpha plus minus alpha, and the minus state you can say is minus alpha minus minus alpha. They are orthogonal now, and this defines your two-dimensional subspace. So this was first proposed by this paper, right? Cochrane, Milburn, Munro in '99 already, so it's kind of an old idea. But then in 2014, there was an interesting paper by Merheim and collaborators where they proposed to use this encoding of the qubit in the harmonic oscillator, but now add two-photon dissipation to the process. So add a dissipator whose jump operator goes as a squared, the annihilation operator square minus alpha square. And the way to do that is just to create some nonlinear optical, like free-wave mixing interaction between your bosonic mode and some other modes, which can be done in superconducting qubits, for example, using a transmon or a transmon-like structure, right? So a nonlinear element there. And then what you can find is that This dissipation, this engineered dissipation, has two dark states, and they are exactly alpha minus alpha. So they are stabilized. And this you can compute in semi-classical picture. You can see that the probability of going now from alpha to minus alpha, a bit flip error from 0 to 1, given this two-photon stabilization, if it's sufficiently large, this will be exponentially suppressed in alpha square. So now, the probability of bit flip errors is exponentially suppressed in alpha square. There is still phase flips, right? So if you have like a photon loss, A, you still go from plus to minus. So there's still phase flips. There is no protection to phase flips. In fact, this two-photon dissipation, actually, in fact, because of like bosonic enhancement, the phase flip probability of error increases with alpha square, but only increases linearly. So now you have bit flips, they're exponentially suppressed in alpha square, and phase flip are only linearly increasing in alpha square. So what do you do with this process? You bias the error. Your error becomes very biased. And now, you can first try to correct most of the X errors, and at another level, only correct a little bit X errors, the remaining X errors, and the Z errors, right? So you can use, for example, a strip surface code or a rectangular surface code. And in the most extreme case, which won't give you, arbitrary protection, but can be an interesting experiment, you can do a repetition cat code, right? You correct X error using the two-component cat code, and you correct Z error using a repetition code. So let me just go through this. This kind of dissipative cat code has been implemented in the lab, like many experiments by now. So in 2014, there was the first realization by Lectas and collaborators, but we didn't see this bias yet. So the parameters weren't like appropriate for that. The same for these two other experiments. Then 2 years ago, there was the first experiment where there was a demonstration that it could increase, that it could reduce the bit flip error rate or increase, the bit flip lifetime, right, a lot. So this was this kind of plot that they got, pretty interesting. This is the time for bit flip errors. And initially, the resonator, it was just a strip line resonator on a plane, was like 2 microseconds lifetime. So, in 2 microseconds, if you have some Fock encoding, you have error there. And then they see that once they have this two-photon dissipation and start increasing alpha square, it will go up to 1 milliseconds. And then it will stabilize because there will be some thermal heating from the transmon affecting the phase in the resonator. But they saw like this exponential improvement, right, with, a 4.2 factor per photon up to 1 millisecond, which was nice. Then recently, this kind of the same team, they got up to 127 seconds, right, which is like a really huge improvement, right? There was a price to pay that, they had to do things in a particular way, which actually the exponent was much smaller, was just like 1.4 per photon that you add. As a result, to get those numbers, you need a very high photon number. And at this very high photon number, won't be useful to, it might be a good classical memory, but won't be useful to actually build a logical qubit, right, a quantum qubit, because at this level, it's not possible to correct phase flip errors. Phase flip errors become very, very likely. So kind of it's very interesting experiment, but, to the next step would be to kind of try to go even beyond 1 millisecond, but try to get a good increase right, a good slope for this like curve, right, in log scale. And the theoretical increase is like around 7.39 per photon, which is this exponential -2 alpha square scaling. So we built in the lab here at AWS this a similar system. There's some modifications in the beginning of the year. We have been improving since then. So this is a picture on the right what we built. I don't want to tell you too much about it, benefit of time, but there is like it's similar to the French experiment, but we also add a tunable coupler between the transmon and our readout resonator for improving performance and a few other things. So we started from 10 microseconds. This should be microsecond C1 time for the readout resonator. So and then once we started screening alpha square, we went up to like 1 second. And if you do the math, this is actually getting close to this theoretical 7.39 scaling per photon that I mentioned before. So it's kind of like the performance that we expect. Theoretically, we're seeing this in the lab, and I think that's exciting. And this leads the way to the experiment that we're building now, that I want to just mention, what we're doing, and I'll give you the results once it's ready. It's not ready yet. But we like to build this repetition cat code. So this is kind of a layout of the experiment that we're trying to do. So we have, here, the dots, they are resonators, right? So a repetition code, this is 9, for example, you need 9 resonators for data qubits, and you need 8 ancilla resonators, right, for the ancilla qubits. You have to do CNOTs between them. And then the way we propose to do CNOTs is to use, okay, so actually, sorry, let me correct one thing. So the data qubits, we changed the scheme a little bit from what was proposed in literature. Like the yellow data qubits, they are resonators, but the kind of brown ancilla qubits, they are transmons, okay? And then we do a CNOT gate between transmon and a resonator. We found a way to do that in a bias preserving way, which is also better and faster. And then this kind of squares, they are tunable couplers that we have to use here. And we also have some transmon for readout, which will be this triangle. So that's kind of the system that we're building. We have it, actually, we're measuring it now, and we need a few iterations, I think, to improve the performance. But that's what we're trying to build. And the idea is that we think this is, there's other ways, of course, and there's work like, in ions and recent work from Google and IBM, where people are trying to build a logical qubit, right? And a logical qubit that, for example, right, goes beyond the break-even point when the logical probability of error is more than the physical probability of error, or sub-threshold behavior, where it's a drop-off error rate with distance and many milestones, right? But basically, we want to do the first step of building a fault-tolerant quantum computer, which is to get a logical qubit out of many physical qubits or many physical components, and show that the performance is somehow improving there, right? So that's the first step. And we think this repetition cat code is an interesting candidate, and that's kind of what we're doing, and where we want to get some results in the near term. Okay, so moving on, right, in this strategy, if you want to build a quantum computer out of this, repetition code might not be enough because there will still be some X errors that you cannot correct on the cat level. But what you can do is you have a still, this will lead a bias to the X probability of error and the Z probability of error, and then you can tailor your surface code to that, do like a rectangular surface code or a strip surface code, and try to get some benefits. So this paper that we worked out 2 years ago and was published recently, we did this exercise of computing everything, not using E&M cavities, but using acoustic cavities, but it'll be kind of similar with E&M cavities. And we saw that, if we can get as good error rates for the physical gates as we can do for transmons, we could get kind of like from 8 to 10 overhead reduction, which is great. But we also found that with this particular cats, it's very hard to get good gates with which are bias preserving. So this is a drawback of this approach. And that's why we kind of went to this transmon ancilla approach that we are investigating now. So some theory work that we publish soon shows that with this transmon ancilla, this gives a much more reasonable scheme. And therefore, it's kind of subtle and depends on the experimental results we get. But we think this might indeed be an interesting way to potentially build a quantum computer. So just to sum up things, so quantum error correction will most likely be needed for prime time of quantum computing. I think this kind of emerging consensus right in the community after a little bit of maybe people getting too hopeful about NISQ, right, and near term. The QC overhead can be very steep, right? It's not steep, so that's a price you have to pay, unfortunately, but we don't have another way. And bosonic qubits might offer an attractive alternative for hardware efficient quantum error correction, but we don't know yet, right? So the jury is still out. There's still a lot of experiments and theory understanding that we have to do to see if this is a better approach than just using transmons or just ions or whatever and scaling up. But I think it's an interesting research direction. And with that, I thank you, and I'm happy to take any questions you might have.
Thank you very much for a very nice talk. And so let me look at the chat to see. And then, okay, there are no questions there, but let me ask, in the previous slide, you were showing the slide before the last one. You were talking about how to reduce the overhead by a factor of 8. Exactly. Right. So how do you reduce the overhead 8 times for the same gate error rates? Because it seems like it's a huge overhead reduction. So this is not clear.
Oh yeah. So this is first is just it's roughly 8, right? From 8 to 10, that's the number we got, depends on many assumptions. But the reduction comes exactly because you do this bias preserving gates and you do these bosonic qubits. So now your X error rate is much smaller than the Z error rates. Right? So you know the bosonic qubits already protect a lot of your X errors that you have there. And therefore, instead of using a square surface code like this, you can use a rectangular surface code like this, right? Where kind of, you know, the width here is like distance 5, for example, distance 3 for your surface code, whereas the other dimension here that grows as usual, right? For correcting Z errors. And then we did some simulations and we got some target logic error rate, I think 10 to the minus 9. And then, you know, putting everything together, assuming the same kind of physical error rates, we got this 8 to 10 overhead reduction. That was our assumptions. We also pointed out it would be very hard to get, you know, similar, at least with this kind of all-cat approach, to get the same error rates, physical error rates as you can for transmons. Doesn't seem very viable. But now we have this alternative scheme, which is more kind of, I think, promising.
When you change the lattice from square to rectangle to line, exactly slide number 30, it seems that you're moving from 2D, like kind of almost stripe geometry, to 1D. So therefore, but if you do 1D, I thought that any defect on the qubits will mess up things because the signal will try to propagate, let's say, on the left or on the right, but it's a defect or impurity or something that doesn't work well, you cannot get around it. So it would seem that the 1D will be more vulnerable to errors and will be less resilient or less robust.
That's right, but like, okay, so the line is just it's not like a long-term solution, right? It's just a first experiment where you can see some reduction. The line, which is the repetition codes, will be a solution only if you assume that your cat qubits already corrected all X errors, right? So suppose there is no X errors, right? They're all corrected on the cat level.
I see.
Then of course you just need a classical code, right? For phase errors, right? Phase flip errors, and therefore you can use repetition code, for example. Of course, in practice, the cat will not correct all X errors, right? And that's why, you know, our estimates in this paper was using this strip surface code, right? This kind of like rectangular surface code. But you still can get a reduction, right? Because you still, you know, if the cat, you know, suppose using the cat qubits, you can get X error rates of like 10 to the minus 5 or 10 to the minus 6, which it hasn't been achieved yet, but I think it's reasonable to assume you could get there. Then, you know, you might only need distance 3 or distance 5, right? For the X dimension here. Whereas for the Z dimension, you have the normal thing, you go like 9, 11, 13, and so on. But then you can still get a reduction, right? Number of qubits. So indeed, the repetition cat code is an interesting intermediate experiment, but it won't be the ultimate way of building a quantum computer, right? But it points to, you know, makes the point that if you bias the error on the cat level and correct a lot of the X errors on the cat level, you need less, right, overhead on the surface code level, right, for getting a particular logical probability of error.
People look at the surface code or bosonic codes by looking like a bilayer system. So you have a 2D system of qubits, and then on top you have another second layer. So therefore they could just talk to each other like bilayer graphene. And then has this been studied, at least theoretically? Like, what advantage do you get by having not a square array of qubits, but a cubic array of qubits? Because then you could just correct errors, not only looking at what's happened on the left to the 4 different directions or ancillary, but you could look also up and down. So you to increase connectivity, because some people are moving more into the 3D electronics, essentially in the future, like 3D interconnects. And
sure, yeah,
if you could do like 2 beautifully controlled system, and you could just, I don't know, theoretically at least connect them in 3D, will that give you a massive reduction on error rates or not?
I mean, if you could do 3-dimensional codes, it's kind of interesting. So in terms of the thresholds, it doesn't improve so much in terms of what we know, but you could implement some interesting codes like color codes. And so for example, if you can do 3 dimensions and your physical components are good enough, kind of like 10 to the minus 4 level, then indeed you could do something things way better with much less overheads. But at the 10 to the minus 3 error rates, then even 3 dimensions is unclear if this would be it will give a gain.
I see. So you need to have for 3D something like 10 to the minus 4 plus 3D, then progress will be faster, will be much faster.
As far as we know, of course, there's a lot of things that we don't know, but indeed, then there'll be very interesting codes like color codes, right? There's like some versions of surface codes where you would get some more efficient constructions. Yeah.
There is a question here by Shiladitya Mal on the question, is there any difference between the error correction techniques required in quantum computation and in those used in quantum cryptography?
So yes, because error correction using quantum cryptography. Let me see. There is so in quantum cryptography, the way that error correction appears is that you have a communication channel, right, where you want to send some quantum information to establish some EPR pair, or right for doing BB84, but there is noise there, and therefore you have to protect right from noise in this optical fiber, for example, and then encode the information in the code, right? So kind of so you can do, and there are many ways of doing that, right? But it's okay, you have to be a bit careful here. But the way that people usually think about that is that the most of the noise will be in the communication channel, right? Not in the encoding and the decoding. So the encoding and the decoding process, there'll be any noisy too, but there'll be way less noisy than the communication during the optical fiber, right? So therefore, it's not about fault tolerance, right? It's just about error correction, right? Whereas for quantum computation, it's about fault tolerance, because there is errors everywhere, including the encoding and the decoding. And that's why the surface code is a very good alternative. But if you just want to establish like an EPR pair, you wouldn't use a surface code, right? So you use some other quantum error correction codes and effects. You just do entanglement distillation, right? That's what the typical approach does, right? So you send many EPR pairs through your optical fiber. You have some quantum memory in the end. They get noisy, but now you have many noisy EPR pairs there, and now you do what's called entanglement distillation, entanglement purification, and from these many noisy EPR pairs, you get one EPR pair which has better fidelity, and then you can do teleportation, and you can extract, you can measure, and can get your secret bits, right? So even though in theory, like it's the same theory, and you could use a surface code to encode and send through optical fiber. In practice, it's not the right thing to do, right? Because it's a very different setting.
I see. Okay, so therefore the answer here is thank you very much. Okay, good. So it's taken care of. Any more question? There's a last one. Could entangled gates between logical qubits propagate errors while performing quantum error correction? And if there is a short answer, it would be good to start with the next speaker, because
sure.
we're a bit late.
So right. So it's a good question, right? And if fault tolerance scheme, that's exactly what it cannot happen, right? Or the propagation of error has to happen in a very controlled way. So transversal gates do exactly that, and that's why we want to do transversal gates, right? In error correction, usually there is no universal way that we cannot have a universal set of transversal gates, but then we do transversal gates, which is propagation of errors do not happen or happen in a very controlled way. And in addition to that, we do what's called magic state distillation to get the extra gates. And again, we handle this propagation of error in a different way, and they combined, we do get the fault tolerance. So you can write to me, I can give you more information later about this.
Okay, great. Well, thank you very much for a great presentation and for the handling the questions here so nicely.